supposed to introduce the lecturer? I don't think so, actually. Okay.
I can introduce myself.
Oh, yeah, you already introduced yourself. Okay, good.
Glen Evenbly. For those of you who don't know me, I'm from University of Irvine at the moment, working with Steve White. Most of you have probably heard of Steve White. He's the guy who did DMRG back in the day. Yeah, so I'm actually going to depart from what is listed in the booklet, what I originally said I was going to talk about today. So today is more about a comprehensive introduction to tensor networks themselves, and tomorrow I will talk about entanglement, renormalization, and the MERA. Okay, so I've just drawn up here a very abridged set of things tensor networks can do. So originally, with DMRG, this was a numeric tool, a very successful numeric tool for give me a Hamiltonian, I run some numerics, I give you good estimation of the ground state properties, maybe some later on some time evolution and things like that. And they're very successful in that you could do strongly interacting electrons, frustrated magnets, things that would be very difficult, say, with quantum Monte Carlo, which is still the main sort of thrust numerically, is these situations that are hard for Monte Carlo. But since their introduction, people were looking at them more theoretically as well as just general models of many-body systems. Like by learning about tensor networks, I can learn about the possible phases of matter. So one-dimensional gap systems were classified based upon tensor network description. People are thinking about tensor networks now in relation to ADS-CFT correspondence. So this is correspondence between gravity and conformal field theories. So holography, and just very general things like that. So these are people on this side, sort of very mathematically based and very numerically focused people. You also have people now thinking about tensor networks in relation to machine learning, error correction codes, data compression, which I talked a bit about yesterday, big data analysis. If you have a big set of data you've gathered, you want to find the correlations in there. A lot of people outside of the physics community, mathematicians, engineers, they're starting to, well, that they were already paying a lot of attention to these things. Let me just say a bit more about this. So I'll try and write as legibly as I can. If I start writing very poorly, please let me know and I'll try and correct it. So research in tensor networks. What's going on at the moment? So there's this very theoretic component, as I've said, very mathematically minded people asking sort of what can they do in a very rigorous way. So deriving scalings of accuracy, sort of asking at a very fundamental level what tensor networks are suitable for modeling and why. You have sort of the very, I'm more in this category, the algorithmic, so new methods, new situations to apply tensor network, so new methods and new situations I want to apply to. Also, a large sort of part of this is coming up with more efficient algorithms, better ways of doing things, so forth. And there's sort of a very applied community as well, focusing on this sort of implementation, actually using them to study models of interest. Okay, so yesterday we saw sort of in the research talks presented in the symposium, we sort of had a whole mix of all kinds of these things. If you do want to go into research in tensor networks, there is a very broad spectrum of things you can look at, whether you're very sort of mathematically minded or you like programming. There are many things you can do. Okay, so So the rest of the talk will be a very sort of hopefully comprehensive introduction to tensor networks. Just for my own, just so I have a better understanding of the audience, could you please let me know, say raise your hand if you are new to tensor networks, if you've not worked in them before. Who doesn't know much at all? Raise your hands. It's okay. So this will be really geared towards you. Hopefully there will be some things even people familiar with tensor networks may learn. Okay, so let's just start off with some refreshing of the notation and some of the technical details about how you work with tensor networks. So as we've seen before, a vector, say vi, is just represented as a single index, a blob with a single index, a matrix, Ij has two indices, tensor Ijk. It's a three-index object, so everyone is probably familiar with this. We've seen it in many talks. And of course, shared index equals contraction. So sum over j, ai, j, bj equals this. Equals some new vector, say we can call w if we wanted. Okay. Of course, the whole point of this notation is we're going to get into much more complicated situations than this, and then this graphical notation becomes much more important. Let's have an example here. Example, if I drew this, what does that represent? Can anyone who's new to tensor networks have a guess what this diagram represents? Yes, but what if I was writing the equation for this? What would I write? Trace of
three matrices.
Yes,
the three matrices.
that is correct. So this is each of these guys is a matrix, two indices. When I write those three matrices multiplied together and then sum up the remaining index. So this is just the trace of A, B, C, where these are understood as matrices in this case. Shaping. So the key sort of, one of the key operations we want to do with these tensors, so imagine I have a tensor of many indices. What I want to do, something that will be very important, is being able to put this guy as a matrix across any partition. So any sort of bipartition, any grouping of the indices, I can turn it into a matrix across this partition. So this is some chi, if indices are chi-dimensional, this is chi by chi by chi tensor. Everyone see over here? I should stay away from this side.
Yeah, we can see through the screen. So.
Okay. And this, so now this guy is a chi cubed by chi squared matrix. Okay, so dealing and doing tensors in a language like MATLAB or Julia or Python with SciPy and NumPy, is a very good choice because these tensors are sort of inbuilt objects of these languages, these manipulations that turn a tensor into a matrix. So in MATLAB, these are called reshape and permute. These are built-in operations as well. Okay, so any partition I choose, I can turn it into some kind of matrix. And so if this guy is A, I, J, K, L, M, I'm going to denote this guy with brackets and the indices. Okay, so denoting I've made it in a matrix across this partition. Okay, go over here. So let's consider binary tensor contraction. What I mean by this, so binary is the contraction of two different tensors. Okay, so let's say have some A over here, and I want to contract it with some B. So I have a whole bunch of indices, which maybe I won't label. How you do this in practice, or how I would recommend you doing this, is first reshape into matrices. Okay, so I have these tensors stored in my computer. I want to do some contraction. First, I group them into matrices across some partition of indices to be contracted and indices that are open. Then, okay, so we'll just draw it like this, where I put legs together. So these are all grouped into a single leg now. Then I do my matrix multiplication. Okay, so this now goes to that, and then what I will do is I will reshape it back. Okay. Reshape back. Okay, and so this is not a huge point, but computers handle doing matrix multiplication in general much better than doing a summation over an index. So when you do it this way, so rather than just explicitly programming it as a summation over these indices, when you do it this way, you can use the BLAS libraries. It will go much quicker. So that's kind of a semi-important point. What is the cost of doing this? So cost of, let's just say, draw it like this at the moment. Cost of doing this contraction between A and B equals A, B over A and B. So here I'm using A to denote the total dimension of tensor A. What this means is the product of the dimension of its indices. Okay, so here A equals chi 5, assuming high-dimensional indices, and A and B is the total dimension of the shared indices. Okay, so the total dimension of the indices that are shared between these two tensors. So in this case, cost of AB equals chi 5 times chi 3, the dimension of B over, they share 2 indices, this is chi squared. Okay, this together equals chi 6. So doing this tensor contraction, if these are all chi-dimensional indices, scales as the 6th power of the Bond dimension. In practice, when you're doing tensor networks, this is an important aspect, is keeping track of how your algorithm scales as a function of the various dimensions in play. Often you have several dimensions you need to keep track of, so forth. Okay, so let's try a network contraction. So imagine I'm going to give you some example here. A, C, B, say I, J, L, M, K. Let's say this is an example of some network we want to evaluate, some new tensor D, I, K. How are we going to do this? Okay, so we could just write this down. So D I K equals sum for A, B, and C over these internal indices. Do it this way. Does anyone know why this would be a bad idea? So in terms of programming, this is something you could do. You could just have loops that loop over these indices, do this contraction. Doing this directly is expensive. You usually don't just want to do this giant summation over. If I have a network with many internal indices, I'll have a huge dimension.
Are there regimes for the dimensions where that's better to do than reshaping? Is the reshape as well?
No, it is always, you can show in terms of the number of multiplications you can do, it's always better to evaluate, or at least as good to evaluate as a sequence of binary contractions. So there is some, so in terms of cost, it's always better to just do a sequence of pairwise contractions. There's I think one example you can come up with where in terms of the overall memory you need, it's better to do it as a summation than pairwise contractions. But overwhelmingly, this is the more useful case. Okay, so do it as a pair of contractions. So we evaluate this network by doing some contraction, pairwise contraction between, so for instance, we could put A and B together and then put tensor C with them like this. So this would give us our D. Or we could do a contraction between, say, tensors A and C with tensor B. Give us the same tensor. So now, here is your exercise. If all of these are dimension chi, work out what the cost of these guys are. Cost. And anyone tell me? Any volunteer? Kenji?
Kind to the force.
So
Which one?
At first, sequence we need to construct A and B.
So A and B is
Is
1, 2, 3, 4.
Yeah.
Um,
The second step we need 1, 2, 3, 4.
second step is second step is also 4.
Yeah.
So yes, that's correct. So this is 2 times I to the power of 4. Let's look at the other way. If we're putting A and C together, look at the cost. We have 1, 2, 3, 4, 5 indices involved. It's chi 5. When we put B with it, so A and C are 1/10, so we have 1, 2, 3, 4 indices involved. So this is chi 5 plus chi 4. So what we have here is a very important realization. Order of contraction matters. Okay, so no matter how I do this contraction, I always, if I do it correctly, I always get the same output, but the amount of effort it requires to get there may depend on which order I do these contractions. So in general, so when you program this in your computer, you have to think about what is the optimal order. This can get very tricky if you have a big network with many tensors and many different dimensions in play. So here, as we said before, people have made some code to kind of simplify doing these numerically, working out which is the best way to do it. I'll just write down some of these codes here. So I have a very, very basic tool that I was a part of. So this is for MATLAB, a function called mcon, which is just a very, very basic tool to allow you to do tensor networks more efficiently. So this is that R5 1402.0939. As we heard earlier, we also have the Uniten library from Yingzhou Kao, which is at uniten.org. So this is C++, a whole suite of tools. So very, very many functions, symmetries, very efficient evaluations, etc. There's also, Steve White has the iTensor library, which is at itensor.org. Again, this is in C++, sort of more DMRG focused, a very a complete, very powerful DMRG code. You can do more general tensor network stuff, but it's sort of developed with DMRG in mind. And as we also saw yesterday, there are many other libraries. Naoki has a library. Ian McCulloch has a library. But here, these are some sort of good choices, especially for beginners. All right. Can I have another example? Okay, let's just really get you familiar with this. Let's say I have a network. This is the sort of typical type of network you may encounter doing a more complicated algorithm. Let's call this A, B, C, D, E, F, G. So a think as a good exercise, can you tell me what order, come up with an order for contraction? This is not as hard as it looks. And what is the optimal cost in terms of chi if all of the dimensions are chi? So just maybe spend a few minutes trying to solve this if you can. It's not that hard. Only God, they get much worse than this if you. Does anyone have an answer for me yet? No one brave enough?
7.
7? I don't think it can be done with 7.
8.
Unless 8 is okay. So I'll just write down one particular way you can do this. So I could do A with D. So 2 4-index tensors contracting 1 index. So this is currently, just keep a tally of how big it is. It's currently chi 7. Let's put a C in there. And now we're doing a 6-index tensor with a 4-index tensor. Okay, so this is now a chi 8 operation. Could throw an E in there, still a chi 8. F. Okay, so we're just sort of working from this side, put this one in, put this one in, put this one in, B with D, and then all together. So I encourage you to work through this at home if you want to follow these calculation costs, but this is the cheapest it can be done directly. And this is one contraction order that realizes.
Is the last one G?
Sorry, G. Yeah. Right.
But is there any simple rule which determines the highest order?
No, this is
For a given network, can you simply immediately get the?
I think it is even proved to the NP hard
I
problem.
think this is in general an NP hard problem. So usually this is done, people have written codes that have done some brute force search or some slightly clever brute force search that looks at the more sensible ways. Like once you have a very big network, doing brute force cost is too expensive. I can't explore all of the possibilities, but you can still get just a very good search. You often find what is probably the optimal case, but there's no way of doing it by hand very well. And of course, once you have, if these are different dimensions, then it becomes incredibly difficult to try and figure out the optimal way. And just generally, if you're writing a code, you want to write your code in such a way that the contraction order can be changed very easily without having to write all the code again. So maybe have contraction order as an input, that your code will work with any contraction order that you specify or that you come from another program. Okay, so this is one of the key manipulations of all of these algorithms, is taking a bunch of tensors and putting them together. The other key manipulation is mostly based upon singular value decomposition, sometimes also called Schmidt decomposition. Okay, so this is putting tensors together. this other thing is pulling tensors apart efficiently. Okay, so let's just say we have some A, which is a chi by chi prime matrix. For simplicity, I'm just going to be assuming chi is less than chi prime, less than or equal to. Okay, so the singular value decomposition is a matrix decomposition I can apply to any matrix A that's going to generate me a unitary, a matrix of singular values is called, and another unitary. So this is a chi unitary. This is chi by chi diagonal positive. And this one is a chi by chi prime, you could say orthogonal, or maybe you could also call this isometric. Okay, so this matrix S, say S equals, we'll call, it's a diagonal matrix, we'll call its elements sigma 1, sigma 2, sigma chi. Okay, and graphically you might draw this as A is going to unitary. Often when you have a diagonal matrix, you just put a bump rather than a full tensor. And here is my V or E star. So by convention, the second unitary is usually taken as the dagger, the conjugate. Okay, and this, so this is chi-dimensional, 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 chi-prime. And the usefulness of doing the singular value decomposition is that it will allow us to approximate this tensor in an optimal way with some reduced rank product of tensors. So what I mean by this, first I'll define the norm I'm using. Okay, so we're just going to use the standard, what would be the Euclidean norm if these are vectors, or the Frobenius norm. Okay, so my norm of a tensor A is just the square root of the product of these two tensors, the scalar product. So if these are matrices, it's the trace or generalized scalar product. So graphically, I'll be doing the square root. My A was some 3-index tensor, then it would be this G. Okay, what we can see from this, if we plug in the numbers, is that this trait of this norm equals the square root of the sum of singular values squared.
So why do you have two lines between A and A star?
Oh, this was just if A was some tensor with 3 links, for instance. So this norm is defined for tensors of arbitrary rank. Just take the scalar product of itself, contracting all indices, with the second one as the conjugate.
But the combination of two indices is not represented by chi prime dimensional in X, right? So this is true for matrices. That is not for
So this is
tensor.
this is a good point. I should just stick with matrices here. So it's true. It's true in general if I have an arbitrary tensor and I turn it into a matrix by making any bipartition, then, and do the singular value decomposition, then the norm is equal to the sum of the singular values across any different partition. But no, that's a good point. I shouldn't mix examples. Okay, and so the key point is we can do a truncated SVD. So if A equals sum over some j equals 1 to chi of u ij sigma j v kj star. Okay, so this is just some arbitrary matrix I put in singular value form. So let us define, so for some chi tilde less than chi, let us define A tilde equals the sum j equals 1 to chi tilde of the same stuff we have above. Okay, so we've taken a matrix or a tensor that we've reshaped into a matrix, we've expressed it in a singular value form, and now what we've done is we've truncated this, so the sigma 1, sigma 2, sigma 3, sigma 4, we're only keeping some largest amount of these guys. So I should say this is ordered such that sigma 1 is greater than or equal to sigma 2, greater than or equal to sigma 3. Okay, and what you can show is that this is, so this A tilde has some rank chi tilde. That this approximation we have here is in some sense optimal approximation for this given reduced rank. Okay, so here we only keep chi tilde singular values. So what this means is if I look at A minus A tilde, the norm of this guy, what I get is just the sum of all of the, so the sum from chi tilde plus 1 to chi of all of these eigenvalues I've thrown out squared. Okay, so if my spectrum of, if my spectrum of singular weights phi I sort of decays very quickly to 0, then this approximation for some small rank, if I only take 10 of the values and throw the rest away, this is going to be very good. Yeah. So I would say these are so what we have is we have contractions. Okay, so we've seen how tensors can be put together to form new tensors. We have some notion of SVD, maybe truncated SVD, where we have tensors where we can pull them apart as products of new tensors. So these are sort of two basic operations of all of tensor network algorithms. I would say 99% of all tensor network algorithms are just some appropriate combination of these two operations. So I think these guys are really, they look scary and intimidating when you first see them, but once you understand these two procedures, you essentially know how to do everything. So everything is just some variation of these two guys. Maybe maybe also eigen decomposition and solving other linear equations, but usually just these guys. So do we have any questions at this point? Now is a good time to ask.
What about the precision of lure? I mean, well, normally, look at it, it's invaded the matrix operations, but so normally, when using level 3 plus or relying level 3 plus, I would be careful with condition numbers and things like that. Do these things become a problem, or in some situations would you need to be careful?
I mean, sure, you always need to be careful about machine precisions. I mean, you. Depending on what you're doing, you need to be. I mean, for instance, you don't want really, really small numbers and big numbers in the same tensor when both is, or we don't want like badly scaled problems.
So if I had, for example, a nearly degenerate system, I would have to be more careful.
Sure, depending on exactly what you're doing. Yeah, I mean, these are, I would say these problems are not specific to tensor networks, they're just specific, like these are just the general numeric problems. Like, yeah, sometimes you have to be careful about these things. All right. Okay. So let's get to so let's show you how to get to matrix product states. Okay, so these are essentially the simplest tensor networks. So this is understood to be what the density matrix renormalization group is based upon. So this wasn't known at first, but later on sort of interpreted this way. So my goal is to show you just starting with a ground state that if we have an area law for entanglement, it implies that we have a good tensor network ansatz for this. Okay, so we're just going to start with some lattice, 1D lattice of sites. So maybe these are spin half sites where everyone, I think on my basis, is either spin up or spin down. Let me put a state here. So any state can just be written as a summation over my sites. I have some big index tensor, many indices, and now I have all my individual spins, phi 1, phi 2, phi 3. Okay, so how I would draw this using the tensor network notation is just a tensor, a single tensor with very many legs. So this has 2 to the power of n so we have 2 to the power of n parameters. So obviously this is something we can't solve or can't represent if n becomes anything resembling big. So n above 30, maybe 40 is beyond the reach of current computers. N above 100 is beyond the reach of the universe. This is not a problem. This is not a problem you can solve through brute force means. So you really, a quantum many-body system, you really need to be smarter than just relying on computer brute force power. Okay. So if this is n sites, let's consider for n over 2 sites, let's consider the density matrix, reduced density matrix, rho n over 2. Okay, so this, of course, is just a trace over second n over 2 sites of phi. Okay, and what people have, so people have figured out how the entanglement entropy of this scales in relation to system size. So of course, entanglement entropy entanglement entropy S equals minus rho times log 2 of rho. So what people have figured out, and because this is so important, I might do it on the whiteboard. Okay, so what we know is that for, what you can show is just for a generic state, if I just take this very big Hilbert space and just take a state, a random state, say according to the Haar measure, what I will get out is that S of rho n over 2 is going to scale with n. Okay, so as just a completely random state in this Hilbert space, everything will be sort of equally entangled with everything else. So a block will just scale as the bulk of the block. So this is bulk scaling. What has been proven is a gapped 1D ground state. So we have a local Hamiltonian. So there are some other sort of more technical restrictions on this conclusion, but the general thing that holds in the vast majority of cases is that this rho of n over 2 will saturate at some constant, at least in the large n limit. So this can be, and this is an area law. So it can be understood if I have, so I'm looking at the total entanglement across this cut in the middle. In a gap system, I have some finite correlation length. Only my spins near this cut contribute anything to entanglement, at least in the large scale limit. So the overall entanglement between left and right is bounded in this way. If I have a critical 1D state, what I'm going to have is this half system entanglement is going to scale as logarithmic of, whoops, it's going to scale as, let's say, log n. Okay, so logarithmic correction. Okay, so in the gapless case, in a critical system, for instance, the Ising model and critical transverse field, so most of the entanglement still comes from things near the cut, but I have non-trivial contributions from everything. So even arbitrarily far away, they still add a little bit of entanglement. This entanglement adds up to give a logarithm. Okay, so I think this is a very important realization, is that so these are the problems we're interested in. We're not interested in just solving generic Hamiltonian over this whole system. What we want is we want to solve, like physics of real systems is described by local Hamiltonians. So these are the problems we want to solve, and these are in some sense much simpler than the generic problem. So this is kind of usually stated if I have some sort of very big Hilbert space, so say 2 to the n states. The states I'm interested in looking at occupy some very, very small corner of some relevant states. And these are the types of states that precisely the tensor networks allow you to parameterize.
Excuse me.
Mm-hmm.
Could you explain more precisely about what is a generic state?
So just so I just have all possible states on this lattice. I just choose one at random, say according to the R measure. And then that's what I mean by generic or random state. So, whoops. Sorry, I forgot something. So in talking about truncated singular value decomposition, one more thing I forgot to mention is that we should define, so for a given matrix A, we could define some chi epsilon as the smallest chi, smallest so this will be useful later on, is that we can define some, if I want to keep epsilon accuracy in my truncated SVD, I define some value chi epsilon. So I need some chi epsilon in order to maintain this accuracy. So this is going to be called an effective rank. And in terms of writing it, you can write this in terms of so chi e is such that my square root, my sum of my, from chi epsilon plus 1 to chi, of my singular values squared is less than epsilon. Okay, so sorry, this was meant to go at the end of the previous thing. But this will be a very useful thing to understand is how this effective rank scales. In particular, the next thing I want to show is how this effective rank chi epsilon is related to entanglement and how it scales with the scaling of entanglement. Okay, so imagine I take my state psi and what I'm going to do is I'm going to treat it as a matrix between the left n over 2 and the right n over 2, and we're going to do an SVD. Okay, so I get out in the middle I have my spectrum of singular weights, so this is something I can always do, and now I want to ask the question, what is chi epsilon? What is this effective rank I need to keep across this cut? So what we can realize is that rho the half system density matrix just equals this state where I've traced out the second set of indices. Let's draw that. 1, 2, 3. So here are 2 copies of my state. I've traced out the second set of indices. We know from the singular value decomposition, these left and this right form, they're orthogonal, they form an orthonormal basis, is another way to say it, or these are unitary or orthogonal matrices. So this guy on the right just completely disappears. And I have 2 copies of my singular weights. Okay, is everyone happy with that? Okay, so here we have we see our singular weights from the cut of the state. Here we have the reduced density matrix, and what we can see is that if we say the spectrum of rho, so the eigenspectrum of rho of this rho, if we call this lambda 1, lambda 2, lambda 3, so forth, what we can see is that, so this is just the top and the bottom are just an orthonormal basis. What we can see directly is that, so these eigenvalues lambda I just equals sigma I squared. So eigenvalues of the reduced density matrix, singular values across the cut. Okay. So this is an incredibly useful relation. We've sort of we've understood these singular values as something sort of physically important. Eigenvalues of the reduced density matrix. So these eigenvalues are of course tied to entanglement entropy. And what we can say is that if I have a, I'll do it over here. If I have a density matrix rho with entanglement entropy some entanglement entropy S of rho, what I can say is that the effective rank scales as i.e. is proportionate to exponential of the entropy. Okay, so at the moment this is just a very rough statement. This can be made more precise depending on your needs, but if I have some value of entanglement entropy, which is entropy of this density matrix, I know that the effective rank to approximate this density matrix scales exponentially in S. So every time I add 1 unit of entropy to this density matrix, I'm doubling the rank I need to represent this. You can understand this if you want. Just to give you an example. So, example of a I can give you at least sort of, we can explore this in at least one direction to show that this makes sense. So if I have a density matrix, I call it maximally entangled. If I have a flat spectrum, so lambda 1 equals lambda 2 equals lambda 3. So let's say rho is a chi by chi matrix. Then all of these eigenvalues just equal 1 over chi. It has to be summed to unity, has to be normalized. What is the entanglement entropy of this row, of this maximally entangled density matrix? Equals the sum minus the sum from I equals 1 to chi of lambda I log 2 lambda I equals. Okay, so we have, let's just look at one value to start off with. We have 1 over chi times log 2 of 1 over chi. Then we have a summation over chi identical values, so we get a chi at the front, a minus. These two cancel. The inverse x just pulls a minus sign at the front, so what we get is log 2 of chi. Okay, so at least in this maximally entangled state, we can show sort of precisely that the bond dimension, or that the entanglement is precisely related to the, that we need exponentially large bond dimension to represent some finite entanglement. Okay, everyone good with this? Okay, yeah, this statement as I said, it can be made more precise if you want the exact sort of factors and whatnot in there. But for the moment, this is okay for us. What does this imply in terms of what we've already seen? Okay, let's go back to the whiteboard. So in a generic state, entanglement across this cut I've drawn up there scales as n. What this implies is my chi epsilon I need to cross this cut should scale as exponential of the entanglement entropy, so exponential of n. So in a generic state, we could still take this generic state and try and decompose it in this way. There's essentially nothing, or we don't make any significant gain in doing this. It's still exponentially expensive to try and represent the state. When we have a gap ground state, so this entropy saturates, so the effective rank we need is just going to be exponential of this constant. Exponential of a constant is still a constant, so this in this case we have only small n. In this case we just have the constant, so it doesn't depend on n, so n is large or infinite. So yeah, so even in the limit of n becoming infinitely large, we should still have some finite rank approximation. That still works very well. In this case, so entanglement is logarithmic in n. Bond dimension is exponential of entanglement. Exponential of a log is just going to go as these exponential and these log are not necessarily on the same basis, so this goes as poly n. Okay, so maybe n is still n is still relatively large. Okay, so for gap systems, n can be made arbitrarily large. For critical systems, I have a polynomial scaling in the system size. This is still efficient, but you cannot make it infinitely large and still have a good representation of the ground state. And sort of this, we'll talk about this a lot more tomorrow. This sort of naturally motivates this other class of states called the MERA, which is one of the applications that's designed to better handle this critical case, to be able to deal with this critical case without this growth of bond dimension required for matrix product states. Okay, so this is, let me just recap this part. So just looking at a state, we related the singular values across a cut to the eigenvalues of the density matrix, which relates to the entanglement entropy of a subsystem. So based on entanglement entropy, you can say that this cut is very efficient with small bond dimension. Okay, so of course, okay, what we could do, so we have this phi. What we could do is we could systematically cut this. So first of all, I cut along the first index, and then I'm going to cut along the second one with my SVD. And so forth. Let's call each of these dimensions chi1, chi2, chi3, chi4, etc. So entanglement entropy is bounded, implies that, so bounded entanglement entropy implies that each of these chi, I can sort of upper bound any of these chi by some chi max. And importantly, this chi max is independent of n. Okay, so this is okay, so and this guy is of course what we call MPS matrix. If I was representing this as a formula, this chi MPS is just let's say this is an A, a B, C, D, etc. It's just the sum, the A, over all of my indices, I, B, C, let's do it, I1, S1, S1, S2, I2, S2, S3, I3, etc. Okay, so each of these tensors, for instance, my B is a tensor with 3 indices and a local index. Okay, and what we had is that this is 2 to the power of n parameters. This one down here, while we have n different tensors, each of these tensors have n tensors. Each of the tensors is at most chi max by chi max tensor, chi max squared, and then we have a local dimension of 2 in this case. So this local dimension was d, then this would just be a d factor out the front. And as we've said, this is independent of n, so we've shown that a gapped ground state can be expressed efficiently in this way. This was all very rough in this particular explanation, but all of these things I've said can be made precise. That you can prove that matrix product states, rigorously prove that matrix product states is an efficient ground state for gap systems in one dimension. Do you have any questions about that? Okay, so what I think is a good homework exercise. So for people who want to build some familiarity with tensor networks or just get into them, I think it's so solve Andy Heisenberg for the ground state on, let's say, n equal 12 sites. So this can be done with exact diagonalization. Si2. So take this exact state. So let's perform the truncated SVD across our system. Okay, so take my state, I'm going to do this cut across half the system with my SVD. I'm going to keep chi equals 2, 4, or 6. Let's say 2, 4, or 10 singular values. How quickly, what is the energy of my approximate ground state after this cut, after this truncated SVD? How does this approach to the exact energy? If you do this, in a language like MATLAB or Julia, this entire thing is only a few lines of code, and I think is a useful example of building familiarity with some of these manipulations. Okay. Is anyone going to do the homework? I'll ask tomorrow. Okay, so I have a little bit of time. So of course, what I've explained here, this is not how you implement a matrix product state in practice. I don't start with an exact ground state and try and carve it out. What I do, as it was sort of touched on this morning, is you treat this as an ansatz. These are some just free parameters, so I maybe just initialize these tensors as just some random tensors, and then you treat it as a variational problem, like how can I minimize my energy, how can I adjust these parameters to minimize my energy. So Steve White solved this this variational problem in a very nice way in 1992 with DMRG, which still remains, in a lot of cases, the optimal way to optimize an MPS for the ground state of something, whatever you want to optimize it for. There are a host of other approaches that have been developed also. I'm not going to go into them. And so this is sort of one question people are looking at. in regards to matrix product states and other tensor networks as well, how to do these algorithmic part, how to optimize them, so forth. People are also sort of looking at more general tensor network states. Again, so rather than just a simple 1D structure, I have things like tree tensor networks. So tree tensor network, TTN. I have MERA. I have more arbitrary ones that we'll talk about tomorrow. And the questions, the sorts of questions we want to ask, we'll ask about these guys. We want to talk about efficiency, how numerically efficient is it to contract these networks. So some networks I can contract with some polynomial costs, some networks require exponential costs in the number of tensors, but then so I have to introduce approximations if I want to do this. So questions for more general networks. So you have questions of efficiency. So numerical efficiency. Then you also want to answer questions like what sort of entanglement do these other networks support? What sort of correlations do they support? Things like this. So this is still, I would say, a very interesting area of research. Is coming up with networks design that sort of try and maximize one of these things, or try and improve an area of one of these that previous networks do not do so well in. So that's all I had for today. Now is a good time for more questions.
So your homework is already a little bit beyond the example you gave. I mean, you talked about the gap system, but this, precisely speaking, this is not really gap, right?
Yes. So in this case, if you were to take this a little further and look at larger and larger system sizes, you would see you need to keep more and more singular values, larger rank to maintain accuracy. Whereas if I had, say, a gap system, then the accuracy, beyond some finite system size, the accuracy would become independent of the n. Yeah. But this being said, DMRG still works very good for gapless cases in a lot of considerations. DMRG is numerically very efficient, so I can have a bond dimension of 10,000 dimensions. So by pushing this bond dimension very large, you can reach very large n that you can accurately approximate. So you might ask, well, do we need anything else to do critical systems if DMRG already works so well? And then maybe we'll talk about more tomorrow. So this MERA has some very significant advantages over DMRG for critical systems, and that, for instance, you can do infinitely large systems in a very nice way. You can capture more of the symmetry of the state. You can evaluate things that are hard to evaluate with DMRG.
So I suppose the tensor network representation of a given quantum state is not unique So if you vary some tensors, you may end up with the same state.
So actually, it's not quite true. And so say in this prescription here, the singular value decomposition is a unique decomposition up to degeneracy of the singular values. So I can put this in a unique form. So when I have a tensor network, there's always some freedom in that I can put some, let's say, some X matrix here and some X inverse. And if I absorb these, so this is a resolution and identity, but I've changed these tensors. So you always have gauge freedom, but with matrix product states, with tree tensor networks, there is a unique way of fixing the gauge. So you have a canonical form, and you cannot have two different representations of the state. Well, the same state represented by two different canonical forms. It's not going to happen. In a tensor network with loops, then it's not so clear what's going to happen. And maybe, so if I have any sort of internal loop, then I don't have a canonical form, and it's not clear that the representation is unique.
In the case of the MERA, we can't determine the wave function uniquely.
So you could have two different MERA, so different tensors that represent exactly the same state, and yeah, so this could happen maybe, whereas in this case it cannot happen.
You say the three different property about one tensor network state, so tensor network structure. But what is the difference between the second entanglement and correlation? What means correlation?
So there are some differences. For instance, in a 2D system, so I can have a gap or a gapless. So both of these guys can have entanglement entropy that scales as an area law. So an L by L block has scaling of L entanglement, but this one has 2-point correlators. So correlation functions CL decay exponentially. Exponentially with L, and these guys still decay poly L. So there are some differences between the two. May not be obvious. So just having a tensor network with the right entanglement scaling may not be enough to approximate your state. So what I mean here is you also, for instance, need to think about scaling of 2-point correlators or higher point correlators and making sure you have a compatible structure for them as well. All right. Yeah, thanks everybody.